Okay, so when we last talked about solids and finding volumes of solids using integrals, we were looking at solids that kind of grew up out of the page. We said that these solids had a footprint kind of in the plane. Oh goodness. My mouse wasn't plugged in. They have a footprint, if you will, in the plane. Right? So we would say, okay, there might be a sideways parabola here and the footprint of the function sitting right there. So if I set this solid down on the plane, it would fit inside that parabola, and then they would tell us what the cross sections looked like. So maybe one cross section looks like a rectangle that's twice as tall as it is wide. So I know that this width is root x. I know that this height then is 2 root x, and I know that the depth of this thing, or its thickness, is my dx. So we can write an equation for the volume of this. That would be the width times the height times the depth of it. Integrate that from where the first slice is to where the last slice is, wherever that may be. And we have the volume of the entire solid, right? So in this method, we know what the footprint looks like. They tell us what the slices look like, and from there we're able to find the volume. The new kind of solid that we're going to create today is a solid that is created by revolving an area in the plane. We call them solids of revolution. For these, we still need that area in the plane, but now instead of that area in the plane being the footprint or the base of the solid, it's going to be the area that we use to kind of sweep out the solid. I always think about this. I don't know why, but I always think of this as like if you were at the beach and you had all the sand, right? If you took like a, I don't know, just like a hard plastic sheet, like a hard plastic rectangle, and you stuck it down on the sand and you turned it, you revolved it, right? If what you had was a rectangle, when you revolved it, what you would create in the sand wouldn't be a rectangle, it would be a cylinder. Right? And the further down in the sand you push the rectangle, the taller the cylinder would be, right? But I have this two-dimensional shape, this rectangle. But when I revolve it, it cuts out a solid. And those are the kinds of solids that we're going to be looking at in this section. Now, the good news about these solids is that their cross-sections are always the same because they're created the same way. They're created by revolving. Okay, so let's go back to the cylinder idea, right? If I stick a rectangle in the sand and I revolve it, it's going to create a cylinder. And I said the deeper you put that rectangle down in the sand, the taller of a cylinder it's going to create. Well, look what I'm going to do because I like to integrate. My rectangle that I'm going to put in the sand is going to be infinitely thin. Its width is going to be dx. Its height is going to, of course, depend on the function, right? So this blue area right here, instead of being the footprint of my solid now, is going to be where all my rectangles come from. So I'm going to take one particular rectangle, and I'm going to write an equation for what would happen if I stuck it in the sand and revolved it, right? What I would get is a cylinder, right? A cylinder up on its side that is so thin. Okay. Now again, we're used to seeing cylinders like this, right? Better drawn than that. This guy is kicked up on its side. So I'm taking this rectangle and I'm revolving it around the axis. So think about what I need to do to figure out the volume of one slice. Anytime you take a rectangle and revolve it, you're getting a cylinder. So every single one of these slices is a cylinder. They don't have to tell us it's a cylinder. If we know it's a solid of revolution, we've got rectangles being turned in the sand. We've got cylinders, also known as discs. Sometimes they call this the DISC method. I need to find the volume of the cylinder. Well, I know the volume of a cylinder. Do you? Okay. The volume of a cylinder is just pi r squared, so the area of the top of it times the height of that cylinder, which in this case is this thickness, right? So it's going to be pi r squared h. Well, look at this graph. Look at this. My h is going to come from the thickness of that rectangle. So your h is going to be a dx, your dx. All I need then is to figure out the area of this circle that I'm going to swoop. Well, pi r squared. Where am I getting my r? I'm going to get my r from the function. So I need pi. My radius, the radius of each one of my cylinders is going to be determined by its rectangle. So this radius is going to be smaller than this radius out here, right? But I can always know exactly how big the radius is. It's going to be determined by the function. Now, in this case, and we'll talk about the variations of this, it's specifically and only determined by the function, because what I'm looking at here, again, the radius is the distance from the center of my cylinder out to the edge. And that is key, right? When I'm talking about my radius, I'm talking about the distance across my cylinder. Maybe that's going to be defined just by the function. Maybe we're going to have to tweak it. But we'll talk about that more as we go. Okay, so long story short, you're creating a solid of revolution. Your regions are always, always, always going to be cylinders. So your formula to find a solid of revolution is always going to be a pi r squared h. The height is going to be the height of the cylinder, which is the thickness of your rectangle. Okay, so we revolve regions, and in this case, we're revolving around the x-axis. You can also revolve around any line, and we'll talk about that. You could revolve around a y-axis, right? We learned how to integrate on y. So if I wanted to, I could go around the y-axis. I would just have to draw my rectangles this way. Okay. In general, though, we're going to take it around the x-axis. Okay, so if I want to take a region, revolve it around the x-axis, and figure out what the solid looks like, at first I need a picture of the region, right? So I have this line, 2 plus x, and I want to take the region from -2 to 3. So -2 to 3, and I want to revolve that around the x-axis. Okay, now think about this. Area that they just gave me is a triangle. So for those of you who have great spatial abilities and you're able to envision it, think about taking this plastic triangle, right? Thin, 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 paper thin, but super strong. Sticking that triangle down in the sand and turning it. What are you going to cut out of the sand? You're going to cut out a cone, right? It's not going to be a cylinder anymore because the edge of it isn't straight. When you put it in the sand, you put a triangle in the sand, you revolve it, makes a cone. Now, for those of us who cannot picture that, I have a trick. I have a trick for getting a picture of your solid. What you are going to do is you are going to draw the region that you're interested in. So what is that? 3, 5, right? So here's my region. Okay. And then I want you to reflect that region over the axis of rotation, right? So 2, 2, or -2, 0 is going to stay. This point though, 3, 5 is going to come down here and become 3, -5. I'm literally just going to reflect this over. I'm going to turn it into 3D. Ready? Put circles on the end. Look at me, I drew it. Okay, now this end comes to a point, so my circle here would be infinitely small. But that's my trick. And you're gonna, you'll notice when the pictures get tougher, obviously they're not all gonna be straight lines. Sometimes it's tricky to think about what the solid looks like, but this method will work every time. Reflect it over the axis of rotation, put circles on the ends. Okay, so again, I'm gonna remind you, if you created a solid of revolution, my friends, when you slice it, the cross sections, they're gonna be cylinders. There's no two ways about it. So thing is, even if you have no idea in the free world what the solid looks like, you know what its cross sections are going to be, right? Its slices are going to be cylinders, because they're going to come, each slice, each infinitely thin slice of this thing, it's going to come from one infinitely thin rectangle being revolved around the x-axis. So, if I want to find the volume of just one of my slices, there's my dx. I need pi, I need my radius squared, and I need the height of my cylinder, which is dx. So all I really have to do here, even if I can't picture what that whole solid looks like, is figure out what's the radius of the cylinder. In other words, write me an equation for the distance between the center of your shape and the edge of your shape. Translation, the distance between your axis of rotation and your function. In this case, the distance between our axis of rotation and our function, this distance right here, is just our function. This is 2 plus x. So when I'm at 0, the radius of my disk is going to be 2. When I'm out here at 3, the radius of my disk is going to be 5. When I'm down here at 1, the radius of my disk, the radius of my disk is going to be 3. Okay? When I'm back here at -1, the radius of my disk is only going to be 1. It's going to be a small one. Okay? But all of those numbers are wrapped up right here. So if I want the volume of this, I take pi, my radius squared, throw a dx on it. That's one slice, that's one cylinder. Well, I need all the cylinders. So I'm going to add them up. I'm going to go from -2, where my first infinitely small cylinder is, out to 3, where this my biggest cylinder, my biggest infinitely thin cylinder is. That integral is going to give me not the volume of one slice, but the volume of all the slices, therefore the volume of the entire solid. Okay, so I want to show you quickly still on this slide what we do if they say, you know what, I don't want you to take it around the x-axis. I want you to take that same area, but I want you to take it around the line y equals, I'm going to pick -4. Okay, so instead of revolving around the x-axis, I want to come down here and revolve around this line -4. I hope I don't run out of space. I don't think I will. I'm going to run out of space. I'm going to run out of space on my graph, so forgive me, but I'm going to change my axis of rotation so that I don't run out of space. I'm just going to go with -2 to give myself a little bit more space. So I'm going to revolve around -2. Okay, so I still want the same area. I still want the area between -2 and 3 of 2 plus x. So I still want this triangle area. The only difference now is that when I revolve it, there's going to be space in the middle, right? When I reflect it, there's going to be space in the middle. So when I do this reflection, when I reflect these points over my axis of rotation, this point at -2 is 2 away. So I'm going to come down here and reflect it. Okay. This point here is 5, 6, 7 away. So I'm going to come down here and reflect it. So here's my triangle reflected. And let's keep my word. Let's put circles on the ends. What I made? I made like a volcano. Look what we made. We made this shape, and it's kind of like a cone. So I might cut the end off of it though, and then drilled a big hole down through the middle. Made like a tunnel through it. So when I slice this, and we're going to get to this tomorrow, it's going to have a hole in it. But guess what? Its cross section is still going to be cylindrical. The only difference now too is the radius. I want you to see this. This is why I'm looking at this in the first place. The radius of my disc when I create it isn't just going to be the function anymore. It's going to be this distance plus that piece. So my radius of this shape is going to be 2 plus x. Sure, that's this distance here, plus that distance, which is 2 more. So my actual radius, the distance between my axis of rotation and the outside of my shape, will be 4 plus x. I'm saying this now in the very beginning because I do not, under any circumstances, want you to get in your head that the radius of the cylinder is the function. Sometimes that's true. If I'm being honest, it's true more often than not. But it's not always true. And what I've noticed is that people, in the beginning, we see most of the questions, because in the beginning, they can be the easier ones, right? So most of the questions, the function just turns out to be your radius, and then people get, oh, this is easy. I just take the function, make it the radius, done. And then they throw something at you where it's not true, and people get thrown off. So I want you from day one not to think about your function necessarily as your radius. It's just a way to get at it. Your radius is the distance from the center, the axis of rotation, out to the edge of the shape, your function. Okay. So in 2D, the distance from my axis of rotation out to the edge of my shape, which in this case is my function plus 2 more. Okay, let's look at a couple examples. Now, if you are awesome at picturing these, good for you. If you are not awesome at picturing these, I will put this website up in Schoology, actually. It's a little interactive function Revolution website, but if you Google Solids of Revolution and like Grapher, you can find some pretty cool websites where it allows you to create the area, which is what I did here, and then revolve it. And it will actually show you the revolution and create the solid, and you can click it and turn it so you can see it from different angles. So if you're having trouble picturing them, this is one I have used, and it's the one I used to get the pictures I'm going to show you here in a minute, but there's lots of them. If you Google Solids of Revolution, Solids of Revolution Grapher, or Function Revolution, this one says. It sounds exciting, a function revolution. Okay, so here we have the region between the graph of f of x, which is 2 plus x cosine x, and the x-axis. So I'm revolving around the x-axis. Let's just keep that straight right now. Oh no, don't look at those. Ruined everything. Going around the x-axis. Okay. And I'm going from -2 to 2. So that's literally the only section of this graph. This piece that you're looking at is the piece that goes from -2 to 2. Okay. So if I do my trick to picture this solid, what I'm going to have to do is reflect this graph over the x-axis. So that means that back here, this little U shape is going to get reflected up. And over here, this little U shape is going to get reflected down. Now, it does not have to be perfect, right? And I'm not nearly perfect. Don't tell anybody. Reflect that part, and then terrible at this. Okay, reflect that part. Put circles on the ends. What I made. It's like a crazy hourglass, even though it's completely closed in the middle, and it has openings on the ends. Okay. Again, if you're having trouble picturing it, check out these pictures that I created on the internet. Okay. And you'll notice it even has the lines, so it kind of shows you what the slices look like. Now, what is hard to see, or a little difficult to see here, I think, is that kind of the hollowness of it, right? That these ends, there's holes on the ends here, right? This is not a closed end here, right? And you can kind of see that in this graph here that's tilted, that you're kind of looking down the x-axis a little bit. You can see the openings there. But this one on the top, where you're looking straight on at it, it's like a little bow tie. Right? But when you turn it, you can see kind of the 3D nature of it a little bit more. Right. Now, I need to find the volume of that crazy shape. And that's fine. Because you know what I know? I know that no matter where I slice this crazy shape, it's going to be a cylinder. And I know that my cylinder is going to be infinitely thin, in other words, have a width of dx, and I even know where its radius is coming from. It's going to come from the distance between the x-axis and the function. Boom! My radius is 2 plus x cosine x. So if I want the volume of one slice, that's pi, my radius squared, times the height of that cylinder. Dx. Remember, cylinders are pi r squared h. Our h is this. Heights aren't always up and down, remember. Our h is that. Our radius came from the function. So here's what I have to integrate. This is the area, or I'm sorry, the volume of one of my cylinders. I want the volume of the whole shebang. So I'm going to integrate that from where my first cylinder is, -2, to where my last cylinder is, 2. If you wanted to get fancy, you could go from 0 to 2 and double it. What? But it's as simple as that. We're going to write the area of the volume of one cylinder, integrate to find the rest of them. Okay, well, let's take a look at another one. Once again, I graphed just a portion of my function, just the portion I need. So I want to take the graph of cosine x, so just this little piece of cosine from 0 to pi over 4. I'm going to revolve it around the x-axis. Okay, so I want this area right here in the plane. I'm going to revolve around the x-axis, so I'm going to do my reflection, right? Oh boy. Something like that. Put my circles on the ends. I think this looks like a dog bowl. That's what I think it looks like. Okay. Let me show you the graphs that I made using the internet. Look at those babies. Okay, so again, this one, it makes it so much easier to see the hollowness of this thing, right? How there's a hole at the end, right? Now, remember, I'm sweeping this whole area around, so in actuality, this is filled up. The reason I graphed it like this is because I want you to see that this end, it doesn't like come to a point. It's not like a closed off thing. It has an abrupt end, like it's been cut off. Okay. But again, if you look at it from the side, it just kind of looks like an area, but if you turn it, if this was solid, it wouldn't look like much, right? But you need to see this, the general shape of it. See how it's narrower at the top and then it widens as you go down. Okay, so again, I don't actually care what it looks like. All I care about is what one slice looks like. So, check it out. I need one slice. So one little rectangle, right? And I'm going to take that rectangle and revolve it. Right? So what I'm going to get is something that looks like this. Okay. There's my cylinder, right? World's worst cylinder. The thickness is dx. And my radius of this cylinder, the distance from the axis of rotation, So this outer edge is just, over here, my function. So my radius is just cosine x. So if I want the area, or I'm sorry, the volume of this whole thing, I need the volume of one cylinder. So that's pi radius squared times h. Pi r squared h. In this case, my h is my thickness, my dx. That's the volume of one cylinder. I need a volume of all of them. So I want to add all the cylinders up. First one at 0, last one at pi over 4. Donezo. I like volumes of revolution because all the cross sections are the same. It's going to be pi, radius squared, and then your dx. If you can figure out what your radius is, you're home free on these. Before I go, I just want to point out that a couple years ago, somebody pointed out to me that on this problem, I accidentally write the word dog in super cool 3D letters. So if you find that cool, this is the place for you. All right. To the next time we're together, we are going to look at those ones with holes in the middle. And you're going to love it. Okay. All right. Have a wonderful day, and I will see you soon.